Good morning, ladies and gentlemen. We are going to do this on page 103, number 29. No numbers.
No numbers?
No numbers. Okay, I'm going to hop on this side. Number 29, page 103, number 29. A bike rider accelerates constantly to a velocity of 7.5 meters per second during 4 seconds. The bike's displacement during acceleration was 19 meters. What was the initial velocity of the bike? Okay, let's write down some stuff first. Well, actually, yeah, let's write down what variables we have, right?
Yeah.
No numbers, just
information
variables.
mining, right?
Okay, so we've got a bike rider accelerates constantly to a velocity of 7.5 meters per second. So V final, right? We have time, 4.5 seconds. The bike's displacement, so we've got delta X or D. What was the initial velocity? That's what they're trying to figure out. What are we missing here? We're missing acceleration, right?
There's no acceleration.
So if we're missing acceleration, we must be using this equation. Okay, so I would use, if I was going to solve this, D equals 1/2 V final plus V initial times time. And then I'd have to solve it for this. So I've got this 2 here. I'm gonna go ahead and get rid of that by multiplying by 2.
Yeah, you can't get inside those parentheses unless you get rid of that multiplication on the outside.
Yeah, so divide, get rid of these, multiply by 2 on this side, because I did it over here, I've got to do it over here. So I've got 2D equals, oh wait, I got this T, huh?
Yep.
Let's get rid of the T too. Divide by T, divide by T. So that goes right here, they cancel. Okay, so right now I've got V final plus V initial. I'm solving for V initial, this one right here. So let's get rid of this. Opposite of addition is?
Subtraction!
Okay, so 2D minus V final divided by T. Now, does this all go under there?
No.
No.
You got that 2D over T, and then you subtract.
And then we subtract, so let's make that a little more obvious here.
Yeah.
So minus V final. Okay. So now we could solve it if we wanted to.
Says no numbers, though. Well, you're the teacher. You can do whatever you want.
Well, let's do it then, yeah? Shall we?
Yeah.
Okay, let's see what we got here. So let's go ahead and put our numbers in here. So my velocity final, let's see, was 7.5 meters per second. Oh, thank you. I was like, where is he going? 4.5 seconds. My displacement. Whoa. The bike's displacement, 19 meters. It's hard to see this, but you can 7.5, 4.5, 19. Okay. So let's plug these in. So velocity final, so 7.5 meters per second divided by, so 2 times the distance. I don't need that parenthesis. Times 19 meters divided by, what was it on the T?
4.5 seconds.
4.5 seconds.
And now you're going to have to put parentheses around that fraction.
Yeah, definitely. So here we go. Let's go ahead and plug it in. So parentheses, so 2 times 19 divided by 4.5, close that parenthesis, minus 7.5, and I get it equals 0.94. What are my units here? Meters divided by second, meters per second.
Meters per second.
Velocity, okay.
Cool.
Cool, moving on.
Yep.
Okay.
We just used that.
We just used that. Okay, good job. Next, read page 92 and understand the example problem.
Don't just look at the words, you.
Understand it. So I'm going to go ahead and hover over this, and so that way you guys can get a clear view of what's going on. You're also going to need this up here. But a better way to do this might be to pause the video and go to the library, find the e-text, and find it in there. We are in chapter 5, page 92, the example problem. Read it, understand it.
We're going to take a break. Let you do that.
Let's take a look at it. It says find the displacement of the plane in figure 511. So here is figure 511.
What is that right there?
So this is a velocity versus time graph.
Oh.
And we see we've got this line right here, and the slope of the line here, we can see there's no slope. It's 0.
Yeah.
Right. And what does that slope represent?
The rise over the run would be the change in velocity over the change in time. What is that?
Acceleration.
Oh!
Yeah. So we've got a constant velocity here, which is actually at 75 meters per second. Sweet. And that means that we are not accelerating. Zero acceleration, no slope. Okay, so what else do they talk about? So they say to find the displacement of the plane after 1 second, 2 seconds, 3 seconds. So after 1 second, 2 seconds, and 3 seconds. It says the displacement during a given time interval is the area under the curve of the velocity versus time graph. So
What shape is that green thing?
this right here, my friend, is a rectangle. Yeah. So we can find the area of a rectangle, right?
Yeah.
Yeah, it's base times height, yeah? So if we calculated the area of this 1 times 75, don't we have that on here? Okay, 1 times 75, we would get the displacement.
Oh.
Doesn't that look familiar? V equals d over t, we can solve for displacement, right?
Yeah. Did we do the thing out in the quad with a stopwatch and measure distance
Oh
with a
yeah,
stopwatch?
yes. We measured distance with a stopwatch, and we calculated our average walking speed. And we measured the time it took us from go to point A to point B or whatever points we chose.
This class is so much fun, I can't stand it.
So this is all making sense, right? And if we wanted to know for 2 seconds, we could do 2 times 75. For 3 seconds, 3 times 75.
And that's what they did, and that's the area under the curve.
Yeah.
But it's not a curve, but it's called a curve.
Yeah, we're gonna call it a curve. Okay. So the velocity versus time graph is the acceleration. Oh, speaking too fast. Velocity versus time graphs. The slope is the acceleration. The area under the line equals the displacement. Gotta know it.
That's what we just talked about. That's simple.
Simple enough. Okay. Oh, back to the book. Page 97. Okay. Page 97, slopes. And I believe we're looking at figure 514, right?
Oh yeah.
Okay.
What are we looking at here?
So again, what type of graph is this? Velocity versus time graph. Not position, velocity. Okay, and so we know the slope of the line is our acceleration. And so we want to know what's going on here in the slopes. So as we go from here to here, it looks kind of like we've got this straight line right here, right? No curves.
Right.
Straight line. And so we have our velocity is increasing. What about our acceleration?
Well, you'd have to know the final velocity, original velocity, and the time to find that.
Oh, can we do that?
Can you get that off of there?
No, we could do it. Okay. So are we gonna calculate the slope for every single segment here?
Except for the last one.
Okay. Yeah, the last one's curved. It's kind of funky, huh?
I'm gonna do that one.
Okay.
Don't make me.
Okay, so let's go ahead and take a look at this. So we know we gotta calculate the slope, and the slope is the acceleration. We know v final minus v initial over t, right? Yep. Okay, so let's go ahead and take a look at this. So for this first line segment, my final velocity, and velocity is right over here, is gonna be 10 meters per second.
Oh, sorry.
Meters per second minus, and my initial was?
0.
Meters per second. Divided by, how much time did this take? This is 10, so that must be...
Must be 5 seconds.
5 seconds, okay.
10 minus 0 divided by 5.
That is two, right?
I think so.
2, okay, what are our units? Meters per second per second. Did we already talk about this?
Yes, we
Yeah,
did.
So it should be 2 meters per second squared.
All right.
Okay, so the slope of the line right here, 2 meters per second squared. Okay, let's take a look at our next one, the next time segment. So again, acceleration equals final velocity minus initial velocity divided by t. I'm gonna put it right. We're gonna go a little bit down here though.
Right.
Okay. All right. So, okay, what do we notice about this? Do we even have a slope?
I can tell you where that slope is, but I'm not going to say it out loud. But
Okay.
let's just, what's the original and final velocity?
Make a prediction here. Think about what it should be. But my final velocity right here is still 10 meters per second, and my initial was, well, it's
That
still
looks like 10 to me.
10 meters per second. Is this gonna be what you think
How
it's
much
gonna
time
be?
is that?
From 10 to wait, hold on.
Actually, that's
from
from
5 to 15. So that's
2
10
seconds.
seconds. Okay, so
10 minus 10 is,
that's a 0 on top, right?
I don't think we need a calculator.
Yeah, we're gonna say 0 meters per second squared because we have 0 divided by 10.
And that slope is horizontal. It's flat. It's not a,
Yeah.
there's no slope. Slope is 0.
Yep, it's not working for us. Okay, we're
One
gonna do this
more.
last one. Here we go. Okay, so again, acceleration equals v final minus v initial divided by time. Okay, let's plug this stuff in. So, okay, so right here, that velocity is 4 meters per second minus my initial, oh, that was 10, right? That's
Yep.
10 up there. Meters per
That
second.
slope is downward.
It is downward. Okay, let's take a look. What is that going to mean? So from 15 to 20, so that's 5, right?
Yep.
Okay, so we have 4 minus 10, that's -6, right?
Yep.
Meters per second divided by 5. Oh, are we going to get a negative number?
I think so.
-6 divided by 5, and we get -1.2 meters per second squared. Okay, which makes sense though, right?
Yeah.
Because if we have a negative velocity, our acceleration is going to be negative.
This stuff does not seem hard to me, Ms. Moore.
It's not. Okay. All right. Rock and roll. What is next? Ooh, what's next? A car starts from rest and accelerates at a constant 2 meters per second squared. Where would it be at 0, 1, 2, 3, 4, and 5 seconds? Make a T-chart every day. Okay, let's write some stuff down first. So it starts from rest, which means our velocity initial is going to be 0 meters per second, right?
Yep.
And it accelerates, acceleration, okay, at 2 meters per second squared. Where would it be? So we're given times. We've got 1, 2, 3, 4, 5 in there.
Yeah.
Where would it be? What does that mean we're looking for?
Well, that'd be like the position or the displacement.
Yeah. Okay. So let me grab my little paper to figure out what kinematic equation we should be using.
Well,
Okay.
first of all,
What are
what's
we-
missing?
What are we missing here? We don't have velocity final. So this one is the equation without velocity final. So that means we're going to use this equation right here.
Oh, yeah. There's something wonderful about that equation.
Oh yeah? Oh, I know what it is. So mod plus 1/2 AT squared. What's our initial velocity?
0.
So that means that right here it'd be well,
Make
0
that go
times-
anything, 0 times anything. So it just,
it's just 1/2 AT squared. Okay, should we plug stuff in? Oh,
Well, make a
let's make our
T-chart
T-chart.
first.
Yeah, I was like, well, what are we plugging in here? Okay, so we are making a T-chart, and we've got time and position, right?
yeah.
So we've got T and X, and we want to go 0, 1, 2, 3, 4, 5. All right, so let's see. So we've got, so D is going to equal 1/2. What was my A?
2
2
meters per second
meters
squared.
per second squared. And what was my T? Oh, well, we have to plug it in, right? Well, if I put a 0 in right here,
It's going to be 0.
it's going to be 0.
Yeah.
Okay, I'm going to put that there. What if I put a 1 in? 1 squared is 1. These cancel, right? That's like 1,
Yeah.
right? So 1 squared is just...
Wait a minute. This is going to be easy.
Yeah, so basically the distance, this basically goes away. It's just T squared, right?
Yep.
Okay, so let's go ahead and 2 squared is 4. 3 squared is
6. 9. No, it's 9.
9,
It's
9,
9.
9. 4 squared is 16. 5 squared,
25.
25. Okay, these numbers look good, right? Okay, and just in case you're wondering, I'm going to say actually, we don't even know this, right? Doesn't matter. Is it meters?
Yeah, it's meters.
It is meters. It's always meters. No, it's not always meters. Okay. Okay.
So does everybody understand what we just did?
Yeah, the only thing that's changing is the time in this equation, because we can get rid of this, and well, if 2 meters per second squared is our acceleration, well, 2 divided by 2 is 1. It works out nicely.
Yep.
Okay. Oh, so what do we have to do next?
I don't know.
What's next, Ms. Moore? Plot these points on a position versus time graph, and draw a smooth curved line through them. Okay. So this should look something like... Oh, I thought I was under there.
Should you ask them to do it?
Yeah, do it. Do it now. I do my do the best you can to kind of draw a graph like this. Okay, and this is a position versus time graph, right? Plot your points.
Go ahead.
Okay, do it. And you should have gotten something that looks like this.
That's not a straight line, Miss Moore.
It is not, For our position versus time graph, this is a curved line. You've
Why
seen
is
this
that?
before.
Where'd those numbers come from anyway?
Basically, what we're trying to do is just
Square the
square the
time.
time, yeah.
And isn't that an exponential curve?
it is.
Sweet.
Yeah, just squaring the time. Okay, let's turn this guy back on if we can. Ah, there he is. Okay. Oh, stuck. All right, we've done this. Moving right along here. Oh, we're done. Okay. Oh, we just did this. Describe the slope of your line. It's curved, right?
Yep.
Right, we just squared the time. What does the slope of the distance versus time graph mean?
With a rise over the run.
Rise over the run. Okay, it was distance over time. Isn't that velocity?
Yes, it is.
Yeah, so the slope of our distance versus time. The distance is x or d, whatever, doesn't matter.
Let's go back and take a look at that graph again and see
Yeah.
what the slope does.
Yeah. So here is our graph. And
That's-
what's happening to my slope here?
At the first,
Whoa.
it's not very much.
There we go. So at first, it's not very much. And then right here, it's a little steeper, right?
Yeah.
Slope's getting a little steeper here, a little steeper here, and then it's the most steep right here.
Yep.
So
if this-
what's happening to the velocity then?
It's increasing.
It's increasing. What does that mean?
What's that word?
Acceleration.
Woohoo!
Okay. The slope on a position versus time graph is the velocity. Yes, Miss Moore, we know this. Okay, now calculate how fast the same car would be going at 0, 1, 2, 3, 4, and 5 seconds. Okay, so what are we trying to find now? How fast?
Just add that on.
Trying to find the final velocity, right?
Yes.
Okay. Oh, we're missing that variable too. I'm just gonna say, I'll put it over here.
You could erase that other stuff.
Yeah, should I get rid of it?
Yeah.
So how can we choose what equation? We have all the variables, right?
And what is it we want?
And we want to solve for final velocity. So we want to solve for this one. We've got all of them. Which one don't we want to use? Well, we actually don't want to use distance or displacement because what if we messed up our calculation?
It happens.
It happens. So we'll pretend like we don't have this variable,
All right.
which means we use this equation. So we've got velocity final equals plus AT.
Boom!
Okay. So let's go ahead and plug some stuff in here. It's already solved, right?
What's the original velocity?
Oh, easy. 0.
Woohoo!
Get rid of it, okay? So, the final velocity is just going to be, what was our acceleration? 2 meters per second squared times t.
That's just going to be 2 times the time.
Nice, okay. So, final velocity. So let's see. So 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is
10!
sweet. Meters per second, baby. Okay.
That was easy.
Easy, easy. Okay. All right. Graph these points on a velocity versus time graph. Calculate the slope of this line.
That would be something they could do.
Do it now. Pause it.
Boom.
You should have something that looks like this, and well, what do you notice about the line here? It's straight, not curved. Cool.
Oh, yeah.
Don't forget, this is velocity versus time. We're switching gears here. Okay, it wants us to calculate the slope, right?
Please, yeah.
Okay, what is the slope of a velocity versus time graph? It's acceleration, right?
Well, it's the rise over the run.
Yeah, velocity over time, change in, yes. Of rise, velocity divided by the run, which is time. Okay, so what's our final velocity here?
I
Well,
think it was 10 meters per second from the data.
10 meters per second minus, and we were at 0 to start with. Divided by time, how much time was this?
5 seconds.
5 seconds. Okay, 10 divided by 5 is 2 meters per second. Oh, per second. 2 meters per second squared.
That number sounds very familiar to me.
Uh-huh.
Ba-boom!
Boom, okay. All right, we're looking good here, right?
Yep.
The slope of a velocity versus time graph is acceleration. Slope is the rise over the run, the v over the t, acceleration. Sweet. Calculate the area under the line.
Area.
Ooh, we talked about this, right? We read the book and it talked about how the area under the slope or the curve or whatever.
The book had a rectangle, but that's not a rectangle, Ms. Mo.
It's not a rectangle. Okay, so in order to find the, yes. Okay, in order to find the, what did it say? Calculate the area under the curve?
Yeah.
Okay, so here we go. Here's our curve. So we want to calculate all this.
What kind of a shape is that? Oh!
Triangle, right?
Yep.
Okay, so
Yes.
area of a triangle is 1/2 base times height. You with me on this?
I'm with you on this
Just
one.
like a rectangle, we cut it in half. Okay. So let's see, 1/2 times my base is 5 and my height is 10, right?
Yep.
So that'll be 25?
I think so. 5 times 10 is 50.
Oh, I forgot my units. Bad Miss Moore. 5 was seconds and 10 was meters per second, right?
Yep.
So I cancel these two out and I'm left with meters.
Wait a minute. That number sounds familiar to me.
Oh. Boom, 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 boom. So we got both of
Well,
them.
I'll be dipped.
Woo-hoo. Okay. Are we moving on here?
Let's.
We're making some good time. What's next? Oh, we just said this. The area under the line of a velocity versus time graph is the displacement. And what are these? Oh, displacement equals v times t.
That's like out of the book there on that example problem,
Yeah, it's just stuff from the book. And then we have our kinematic equation that gets us displacement.
which is what gave us that thing over there.
Mm-hmm.
Sweet.
Okay. Here we go. Ooh, some practice problems. Okay, pause the video. I'm gonna go ahead and do some erasing over here. You guys take a stab at this. Starts at rest and speeds up. Okay, so I've got my car. Okay, it starts at rest, which tells me my initial velocity is this. And speeds up to
25.
25. So that's my velocity final. Okay. What was the acceleration?
3.5 meters per second squared. Positive. Yep.
Good. How far? Oh, okay. So it wants to know the displacement. Okay. How far will it have gone when it reaches 25 meters per second? Okay. First things first, make a sketch.
We got it.
We got it done. Draw a motion diagram.
What's a motion diagram?
That's the dots and the arrows, right?
That's right. That's right.
Okay, so it's speeding up. Okay, so that means it's going to cover some more ground. So before it was kind of closer. Oop, nope, right there.
Yeah.
Let's put that one right there. Okay, so.
Sweet. The arrows
Yeah.
get bigger. That means it's
Arrows
going
get
faster.
bigger. Yeah, arrows get bigger. It's going faster. Okay, select an equation and solve. Okay, let's take a look at what we got here.
Well, we got 4 variables. What's missing?
What is missing? It doesn't look like we have time. So there's no time, which means we're going to use this equation.
Aha.
So v final squared equals v initial squared. What is it, plus 280?
Yep.
Tad. Okay. And what am I trying to solve for?
D. Uh-oh. It's not solved for D, Mrs. Bull. How do we do this?
We can do this, okay? Before we deal with the multiplication, let's get rid of this. Opposite of addition is...
Subtraction.
Okay, I feel like the AC just stopped working.
I know.
The things I do for you guys. Okay, equals that, tad. And again, solve for this. So can I just divide to get rid of it?
I think you should.
To undo it? Yeah. Okay. So that equals D. I'm going to go ahead and just plug this stuff in over here. So velocity final is 25 squared. what are my units for that? Just per second. Minus my initial velocity, which is 0. Sweet. That just goes away. Divided by 2 times my acceleration. My acceleration was a positive 3.5 meters per second squared. And you get the calculator. Okay, so I'm just gonna do 25 squared divided by the bottom, which is 2 times 3.5.
You better put the bottom in parentheses.
Shoot. 2 times 3.5. Does that look right? 25 squared? Yeah, okay. And I get 89.3. Okay. So this would be my, that's for distance, right?
That's a distance right there.
89.3 meters. Here we go. So this is 89.3 meters. I think we're done.
That was simple.
Easy. Okay. Another one. Another one.
Well, this is the same car. Something happens. A little puppy runs into the street. Put on the brakes. Don't hit the puppy.
So the same car is traveling at 25 meters per second, right?
Yeah.
When it hits the brake due to, God forbid, a puppy riding in the road, so let's write some stuff down. So it's, okay, car over here. Okay, same car,
It
different spot.
accelerates to a stop.
Ooh, what was the acceleration? Oh, the stop. Let's see. That means that my final velocity now is this.
And that was the original velocity for the brakes.
Yeah. So it was final. Now, like we talked about, it's the initial. Okay, car is traveling at that fast. When it hits the brakes and accelerates to a stop at 8.5 meters per second. That's units of acceleration. But it's stopping. So what do we have to do with the sign there?
Well, I think that arrow's going in the wrong direction if it's slowing down.
Right.
It's got to be negative.
Yeah, like this, right?
Boom!
Okay, so again, how far? What are the displacement, the distance here? Okay, make a sketch. Done. Motion diagram. Okay, so over here we were speeding up. Over here we're slowing down. So we're gonna go boop, 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 boop.
You get closer together because it's slowing down.
Yeah. So if we want to draw the arrows get smaller, get shorter. Okay. Select an equation and solve. Can we use the same one?
Yeah. What would you have to change on what you've got already?
So my final velocity is now
Zero.
0 meters per second squared. Okay, minus my initial here was 25 meters per second. Oh yeah, and it's squared up there. And then I divide it by 2 times the acceleration, negative 8.5 meters per second squared right there, 0.5. Okay, so let's go ahead and do this. So we're gonna say, now should I put this top part in parentheses?
I would,
Right?
because you got to put the 0 in this time.
Yeah. So let's go ahead and put parentheses. So 0 squared minus 25 squared. Okay, then I'm going to divide by 2 times negative 8.5, right? Okay. And I get 36.8.
All right.
36.8.
That's positive 36.8 because the
It
brakes
is.
don't make you go backwards.
No, we're still moving forward, right? But we're just slowing down. So this is 36.8 meters. That's kind of a far way to put the brakes on for hitting a puppy. Hopefully the puppy's all right. Okay, I think that's everything.
I think that's it.
All right, guys, head to the next page for your homework.